Okay, well, thanks everybody for being here, and thanks, Antti. We have today with us Antti Honkela, who is a social professor at the Department of Computer Science at the University of Helsinki, and he's coordinating professor of the research program in privacy preserving and secure AI at the Finnish Center for Artificial Intelligence, as we know. And Antti, up to you. Thanks.
Thanks, Luigi. Welcome all. So today I'll be talking about our kind of bunch of work we've done on accurate privacy accounting for differentially private machine learning. So basically trying to figure out how private are some privacy preserving machine learning methods that are used fairly broadly nowadays exactly. And this is work led by our postdoc Antti Koskela, who has recently left and moved to Nokia Bell Labs. And also other co-authors include Joonas Jälkö, Lukas Pödiger, and Mikko Heikkilä. So before we get to the actual question of privacy accounting, let's start more from basics and what kind of privacy challenges are we looking to solve with these methods, and kind of what kind of questions do these techniques that we've developed, what are they suitable for? And some of the sort of modern privacy challenges with machine learning and data science include questions like how can we share sensitive data without compromising the privacy of individuals, which maybe the poster example of this is the US Census. So the US runs a census every 10 years. They collect lots of sensitive data about people's ethnicities, religion, age, gender, many other aspects. And then they release products that report these in a relatively fine geographic sort of division. And by law, they are required to protect the privacy of individuals. But as sort of technologies for breaking this privacy have improved, it's become obvious that techniques they've developed and they've used until 2010, when combined with other data, you could break these protections and identify a significant fraction of people from these releases. And therefore, there's been now a new approach in how to protect the privacy here. Getting more towards machine learning and sort of use cases people might encounter in their daily work. One question is, how do we make sure that models trained on sensitive data do not remember too much of the data? There's this idea that, okay, let's say that you have a text autocompletion system and you autocomplete the sentence, my credit card number is. You don't want the completion to be someone's actual credit card number. And there is work by researchers at Google who've analyzed the GPT-2, a big language model, and found out that you can actually uncover some personal data that was included in the training set for that model. And even things that were only included in a single document are remembered by the model, and then they can be extracted from it. Another common application is how can we collect anonymized telemetry data from apps? So nowadays, kind of many app developers are interested in how people are using their apps. You don't sort of want to send everything that the users do to the app developer. That would typically be a breach of privacy. But how can you do this in an anonymized way? And the solution to all of these problems basically builds on a technique introduced by social scientists in the 1960s for how to collect responses for potentially embarrassing queries, where Warner introduced this protocol called randomized response. And the idea was that they were doing surveys asking people sensitive questions like, are you using illegal drugs, or have you cheated on your spouse? And the respondents were instructed to answer these questions as follows. First, flip a coin. And if the coin gives you tails, you respond truthfully. If it gives heads, then you flip a second coin and answer randomly depending on the outcome of the second coin. Now, if we work out what the answers turn out to be. Now, assuming your true response to the query would be true, positive, then there's kind of a 50% chance that you will the first coin will tell you to answer truthfully. And then with the second coin, there's another 25% chance that you will answer truthfully. So in the end, there's kind of like a 3/4 chance that you'll answer truthfully and 1/4 chance that you will answer the opposite. And this gives everyone a plausible deniability. So even if you answer true, you can always say that, well, it was just the 2 coins, and there will be some residual doubt to that. But on the other hand, there is a higher probability that the answer will be truthful, and therefore by combining answers from many users, it's possible to find kind of the proportion of people who would have answered yes in a population, even though you can't be certain of any single user's response. This idea was generalized in 2000s into work in differential privacy, which basically extends this idea that we always need this plausible deniability. So regardless of what the data is for a specific individual, you need to have some probability that you will get any outcome, and these kind of ratios of the probability should be bounded. So differential privacy is based on a thought experiment visualized here, that we are running our algorithm M on 2 different data sets that differ by contributions for a single individual. And the definition requires that the ratio of probabilities to obtain any specific outcome should be bounded, and the bound depends on the privacy parameter epsilon here. This turns out to be a very useful definition. It provides protection against adversaries with side information, and we get sort of very solid foundation. It's that has many nice theoretical properties. It can quantify the statistical loss of privacy, and basically also kind of you have this nice property that when you run these combine multiple differentially private mechanisms, the result will also be differentially private, which is something very important for building algorithms based on this. Before we go more into the theoretical results, let's sort of quickly review the randomized response. So just to illustrate that if we sort of generalize it a bit, that we say that there is a probability P that we flip this bit before we release it, then it's sort of fairly straightforward to do the math that the kind of the probability ratio is bounded by 1 minus P over P. And we can sort of work out that the epsilon, what the epsilon will be, and kind of for the randomized response, original randomized response, the probability P would be 0.25, so that would give an epsilon of a bit over 1. But this is sort of just to get an idea of how these, and then when we get to where it's almost very likely that we will be flipping the bit, then the kind of the epsilon guarantees approach 0, and we get very strong privacy. So that's maybe not the most practical algorithm. So here is kind of a much more familiar algorithm for people working in machine learning. So stochastic gradient descent with differential privacy. And this is just to get an idea of how kind of these more typical algorithms can be made differentially private. So the idea is that we have an objective function that is a sum over a data set. And we want to optimize this objective whilst preserving the privacy of the individuals whose contributions who contribute to the objective. And the way this is done requires a few simple differences with the original gradient descent. So first, we compute all the gradients from possibly a subset. And then in order to bound the contribution of each individual, we have to clip these. And then we have to add noise. But that's basically it. So with these small changes, we can make our standard stochastic gradient descent differential private. One big question here is how private will this actually be? So if you run stochastic gradient descent for a large number of steps, you will be looking at the data many, many times over. And it's not an easy task to tell, okay, how much privacy do we actually gain from this? And this is actually the question that our work is about, solving. How private would this mechanism actually be when you run it over many steps? So before getting there, just kind of a quick glimpse of how differential privacy is used around the world nowadays. So 2 years ago, differential privacy was named by MIT Technology Review a breakthrough technology of the year, which they call and say are technologies that will change the way we live and work. These techniques are extensively used by most of the big tech companies to solve problems like I highlighted in the introduction. So telemetry collection, ensuring privacy of shared data, ensuring privacy of predictive models, but also more challenging applications like private federated learning, which allows training machine learning models on data that remains on client devices. And so I quickly pointed to the US Census. So they are kind of in the most recent version, they are also using differential privacy for ensuring the privacy of the citizens. So quick outline. So we've gone through the introduction to differential privacy. Next, I'll go a bit more into the theory of compositions and how can we evaluate the privacy for a run of DP-SGD. First, a bit of background, then about the numerical privacy accounting with Fourier accountant, which is our method, and then concluding with some further developments and other thoughts. So to get started, kind of the basic idea here with these, what I call compositions, which are kind of the foundation for the privacy accounting, is a unique feature of differential privacy is that if you sort of access the same data set repeatedly using differentially private mechanisms, this and release all of these results, the combination is still differentially private, just with weaker parameters. And this is very different from many other privacy definitions. So one broadly used definition is so-called k-anonymity, for instance. And with these, there's typically happens that, I mean, if you're unlucky, it may be that, I mean, if you take two k-anonymous releases from the same data, you can combine them and completely break the privacy. But that doesn't happen with differential privacy, as shown by this theorem that's originally from Dwork et al., from the original DP paper, which shows that if you have two DP mechanisms and you release a composition, which is really kind of, you just concatenate the results from the two releases, then this is DP, and kind of the privacy parameters here, larger means less private. So you just add up the epsilon values for these two mechanisms. This is called basic composition, and it's kind of then the privacy loss grows linearly with the number of mechanisms. And this is actually best possible you can do under this so-called pure epsilon DP, which was what the original definition here was about. This is not very nice, this linear growth here, if we are talking about something like stochastic gradient descent, where we need to run thousands or even more iterations. And therefore, there's been lots of interest in relaxing the definition slightly, which allows us to achieve order square root k growth for k-fold compositions. So this motivates the definition of approximate differential privacy, which for the original definition of differential privacy, we had that for any two data sets differing by one sample. So basically we said in the original definition, there was this no delta, so we just set this to 0, and the requirement was that the ratio of these two densities should be bounded, or probability should be bounded by e to the epsilon. Now with approximate differential privacy, we add this small slack term here. So basically, that mainly makes a difference if you have some very low probability events. So then, if the probability of this is very low, then kind of this might be important. The interpretation of what this means is not easy. There are some papers, even very influential ones, that claim that this is the same as having epsilon dp with probability 1 minus delta, but this is unfortunately not true. So there is no simple interpretation for this. I guess it's mainly, the main idea is that it's almost like epsilon dp, but then there is this sort of small probability that something can be different. And the key point here is that this delta should be very small. For instance, if delta would be 1 over n, where n is the size of the data set, then we could just randomly pick one of the participants and release their data, and that wouldn't be very private. So typically in the original definition, they say that it should be cryptographically small. Okay, but with this thing in mind, now if we move to compositions in approximate DP. So here is a quick summary of composition results for k-fold adaptive compositions. So the assumption here is that we have k epsilon delta DP mechanisms, and we are releasing a sequence of outputs from these mechanisms. And also now here is kind of, these are adaptive compositions, which means that the sort of the future mechanisms may depend on outputs of earlier mechanisms. So this is really kind of sequential in that sense. So just highlighting what kind of work there has been. So if we start from this basic composition in the pure epsilon DP case, we had this k epsilon. Now if we add delta, it becomes k epsilon k delta. So now a big jump here was the introduction of an advanced composition theorem, which basically you increase this delta part a bit by going to by adding sort of a bit slack there. But with this slack, it's possible to reduce the multiplier for epsilon here into square root k times then log 1 over delta prime. And then there is this second order term on epsilon, but usually when you're running multiple comparisons, then your epsilon would be small. So this epsilon squared term doesn't matter. And this is kind of the leading term, is what kind of this epsilon term is what matters more. So this kind of was the standard. There was, then there is kind of a new paper by Kairos et al. In 2015, where they sort of improved this slightly and actually showed that this is optimal. So it's a little hard to see what the difference is, but with suitable parameters, this will turn out to be a little smaller. These are still not very great. So we have this k delta here, which means that the delta would have to be really small to start with if we are doing lots and lots of compositions. And then we also have this delta prime, which might end up being kind of a pretty large factor. But this is the best you can do, kind of, if all you assume about the mechanism is that it satisfies epsilon delta dp with 1 epsilon and 1 delta. But this is actually not true. So most mechanisms will satisfy this epsilon delta dp, not just with a single parameter, but there is an entire trajectory. So you can basically give me a delta, and I'll give an epsilon corresponding to that delta that the mechanism satisfies. And the previous results weren't using any of this information, that you can actually sort of choose any combination of epsilons and deltas. The first paper to actually start using this entire trajectory of privacy profile was by Abadi et al. This is a very famous differential privacy, deep learning with differential privacy paper, where they introduced a method called moments accountant that made things much more practical, because they could basically get this factor log k over delta smaller noise standard deviation, or root log k over delta. And now if you think that, I mean, k is like thousands, delta is small, this log can get pretty big. And so if you sort of then you end up that you have to add like 5-fold less noise or something like that, that is very significant. So the approach they used there was somewhat ad hoc, but it has since been further developed into a full-fledged theory under the name of ReniDP that provides a sort of more stable foundation for this method. And this provides a significant advance over the advanced composition, but recent research has shown that it still kind of provides the absolutely tight epsilon delta bounds. And I have some results later on comparing our method with these ReniDP accountants that show that we can actually get pretty nice improvements still over these methods. But just to give a flavor here, so this is kind of taking the table we had last time and introducing the moments accountant, kind of the approximately the kind of guarantees they get there, that now we don't have this log 1 over delta term, and we don't have the epsilon squared term in the total epsilon. And also we don't have the k times delta, but it's just delta for the total delta, and that also is a huge improvement. Okay, but then how can we solve this even better and kind of really getting to the absolute best accuracy that can be achieved? So in order to get here, we will need some tools which will be defining the exact privacy profile or privacy loss distribution of a mechanism. And this privacy loss function, that is the basis for this, is defined as the density ratio of these outputs of the mechanisms for two adjacent or neighboring data sets. And so this is the same ratio as we had for the definition of epsilon dp. So basically, it's the definition is clear that the mechanism for the mechanism to be epsilon dp, the absolute value of this privacy loss function has to be uniformly less than epsilon, or at most epsilon. We want something more. We want the full characterization of this. So for this, we are looking at the probability density function of this privacy loss function, which is the which we call the privacy loss distribution, or PLD. Now, these PLDs can be used for accounting. So there is a theory, and I forgot to add the references here. This goes a few years back. So there's a theory that shows that the PLD of an adaptive composition is the convolution of PLDs of the components of the composition. And also, it can be shown that the tightest possible delta as a function of epsilon can be evaluated as a maximum of two integrals of this form. So this is basically a weighted integral of these privacy loss distributions. So basically, with this formalism, assuming we know the privacy loss distribution of a mechanism, we can compute these mechanisms in theory just by doing convolutions and then solving this integral. And obviously, these are quantities that can't be computed analytically in most cases, but we can develop numerical methods for dealing with these. So one challenge here is that, I mean, many mechanisms are discrete. So this can't be applied exactly, but it's possible, for instance, to use generalized densities to work out the output also for the discrete case. And yeah, another potential challenge here is that in order to apply this, it's you need to define what are the worst case data sets or mechanism outputs, so that you can prove that this applies for all data sets and not just for a particular pair. Before getting to those difficult questions, so our contribution here mainly looked at the methods for actually solving these numerical problem of how to evaluate these bounds. And our work, what we did was to simply kind of make use of the fast Fourier transform to efficiently compute these convolutions for potentially a large number of convolutions, because if you do the Fourier transform, then a convolution turns into a product. And so the approach is basically straightforward. We just evaluate the PLD on a fine grid, use fast Fourier transform and element-wise power to evaluate the PLD of a composition, and then numerically evaluate the tight delta by approximating the weighted integral, the formula that was given on a previous slide. Now, this is very straightforward in principle. The big question is that, okay, how much error will there be? And I mean, if we are interested in how private these are, so we want a tight upper bound on how much privacy do we lose in this. And to address this, we have to account for potential sources of error, which here come from the discretization and truncation of the PLD and the periodization that's necessary for the fast Fourier transform. And basically, in our papers, we've done the error analysis for these. So basically, we first get exact upper and lower bounds for delta by placing discrete or discretized PLD on a grid. And then we can evaluate the truncation and the periodization errors of the bound by using a Chernoff bound and moment generating function. So there's a bit of math for that particular mechanism, but then these are very general. And then by adding these error bounds that we get to the upper and lower bounds from this first step, we get strict bounds where we can really prove that it will be within these bounds. And yeah, so this was mainly for the discrete case, but this can also be applied for the continuous subsampled Gaussian mechanism, which is the main mechanism used in the stochastic gradient descent by just discretizing that. So here's just some visualizations of that kind of to get a feeling of what this looks. So this is PLD of subsampled Gaussian. And once we start doing the convolutions, we end up in a case where it gets more and more diffuse. And this is one of the challenges for the algorithm, that kind of we, in order to discretize this, we need to kind of set some bounds with they define the region where we discretize it. And now as k increases, then kind of the distribution will smooth out, and there will be sort of we need to broaden the range. Maybe also kind of preemptively answering an idea that, I mean, if you look at this kind of, then there's the question that, okay, what happens if we increase the number of compositions towards infinity? And looks like these are becoming more Gaussian, and that is indeed the case. So there are these sort of central limit theorem type results that can be stated here. But the downside is that they are not really exact. And if we want compositions for a finite number of compositions like k equals 4, then this is not a Gaussian. And if you approximate it with Gaussian, you will get incorrect results. And that's why some methods based on this idea don't really work. Okay, so to cut the long story short, so here is how it works. So we end up with approximations, and as we increase the number of grid points, the computation time will increase. It's going to be n log n because of the fast Fourier transform, the computation time. But we get these nicely converging upper and lower bounds and so the true privacy loss would be somewhere in between. And there's a fairly significant gap between our results and what we get from this TensorFlow moments accountant or these rainy DP compositions that are widely used and kind of that represent really the previous state of the art. Here's another view taking a slightly different look. So now we are looking at epsilons for a given delta. And so it shows that the difference is especially significant in the sort of high privacy regime and a relatively small number of compositions where these rainy DP based methods don't seem to work too well. But then as we go to the kind of really large number of compositions, then the difference becomes maybe less significant. So it's more of an additive constant there, I guess. I'm not sure if we've ever actually done the analysis, what it converges to. So here's another example showing how we can use it for very different kind of mechanisms. So this is doing accounting for what's called an exponential mechanism, which is a technique for selecting an element. And here we perfectly match results from a recent paper where they were doing optimal accounting. But because of the fast Fourier transform, we can actually make it a lot faster if we compute for computing a large number of compositions. Okay, so to sort of give a quick glimpse of what would be kind of the next steps. So just wanted to highlight kind of one interesting current trend of work that we are kind of have been working on recently. So one interesting application for these methods, I mean, I mentioned there were these cases. So the previous work could be applied in a kind of so-called centralized DP case where kind of we have a trusted aggregator who has access to all the data and trains a model and wants to monitor how private that model is. For things like this anonymized collection of statistics and things like that, we need to what's called a local DP, where kind of you don't have a trusted aggregator, but instead kind of individual users add noise to their own data before sharing it with the aggregator. And this is actually a mechanism that kind of our phones, like or Google and Apple, are using to collect data from our phones. One way to improve the privacy in this case that has attracted a lot of research attention lately is to introduce a so-called secure shuffler in between that basically randomly shuffles the messages before sharing them with the aggregator, which makes it much more difficult for the aggregator to associate any single message with a given participant. And in our recent work, we've been working on extending the Fourier accountant to provide exact accounting for shuffling as well. And this is something that sort of hasn't really been possible before. So there has been, well, I mean, there is some work on using RenyDP for this, but again, kind of the exact accounting for shuffling is previously unsolved problem. There's actually a lot of recent work, and I mean, so sort of the first paper on the topic goes back to AISTATS 2020, and this has already been taken up by a few other researchers. So previous NeurIPS, there was a paper by Gopi et al. Who improved our approximation procedure and tail-bound. And as an outcome, they could reduce the number of grid points so that the runtime would be reduced by a factor of order k for k-fold composition. So this makes the method more practical for large numbers of compositions. I already talked about this kind of approximations with the central limit theorem type things. So there was a paper by one that's attracted a lot of attention is this Gaussian differential privacy, which is promoted as a convenient alternative. But the problem is that because they're using this limiting approximation, the results are often overly optimistic. So this cannot really be recommended for use. Finally, there's some very recent work on arXiv by Zhu, Dong, and Wang, who present a unifying theoretical framework for accounting. And they resolve questions like how to find the worst case by defining a concept of dominating pair of distributions for a mechanism that can solve this. Running out of time, but very quickly still. So one interesting dilemma of this numerical accounting is that kind of if we want to get the exact privacy bound for a difficult composition, there typically isn't a simple closed form analytical solution for that. So kind of if you just want to have a mechanism and want to tell others, okay, how private this is, then numerical accounting is very good for that. However, if you're doing theoretical research, often you sort of are interested in getting an expression of how things scale. So these order root k and things like that are very valuable for understanding mechanisms. But these are not easy to get from these numerical accountants. So there's sort of interesting duality here, whether there will be a divergence between the methods used for kind of applications versus theoretical research. Finally, to know that the numerical accountants compute, the way it's defined, computes delta as a function of epsilon and algorithm parameters. This is usually kind of the thing we are least interested in. So you will need to combine it with some search to find kind of other quantities. This is usually not too difficult because the functions tend to be monotone. So, but it just means that there's sort of a bit more computation to be done. With that, I'll just conclude by noting that the PLD formalisms allows computing exact epsilon delta privacy losses for compositions of complex mechanisms. And we get these nice converging upper and lower bounds for many practically important mechanisms, such as ones used for differentially private SGD. That's it. Thanks a lot. I'll just flash a few slides of references here, not to look now, but maybe you can look them up from the video if that becomes available at some point. Thanks.
Oh, thanks, Antti. Fantastic talk. Yeah, really interesting. So we have like 5 minutes left. If anybody has any question, otherwise I have some. Okay, well maybe we wait. Yeah, Anna Korolyuk.
Hi, I'm curious to ask maybe about legislation. So, how do you think, is legislation strict compared to these methods? Is those methods enough to follow the GDPR?
Well, my interpretation would be that, I mean, the DP it would be the best bet for a method that satisfies the GDPR. And there is even some work that sort of studies, kind of formalizes this requirement of the GDPR for not being able to single out individuals, and shows that DP satisfies it, whereas some other approaches like K-anonymity don't. But I guess kind of this is an area where kind of more work is needed to sort of develop an understanding, and also in collaboration with the legal experts. But yeah, I don't really see any other viable solutions that could even in theory fulfill the requirements of the GDPR. Especially one of the nice things is that, I mean, the DP is sort of future-proof in a sense that it will kind of, we can show that, I mean, no adversary, regardless of their capabilities, will be able to break the protection.
Okay, thanks. If there are no other questions, then maybe I have a few. So yeah, actually, so you mentioned that at the beginning, but just to check that I understood correctly. So if it also works with this PLD formalism, so this can be done adaptively in the sense that we don't need to know the K in advance, but it can be retroactively computed.
That is an interesting question. So the theory here actually is for a case where we know K in advance.
Okay.
So if it's adaptive in the sense that K depends on the outputs of the mechanisms, then it's a sort of more difficult case. There is work on generalizing Renyi DP for that case, but not yet this PLD as far as I know. So yeah, that's still open.
Okay, thanks. And then another one related to, so yeah, you mentioned these other approaches in which, so essentially, yes, so one could take this asymptotic central limit theorem approach and kind of get to easier results, but then they are. So I was wondering, so let's say a hybrid approach could be, let's say, to use the numerical to kind of get to some K that would, so check if this is right. So essentially, so you could say that after a certain K, then let's say the central limit theorem would start working. Would be that correct in the sense for a specific process? And so essentially, so one would just need to check essentially with the numerical algorithm whether we enter in that regime, and then after that, people could be using this simpler approach, or that say there is some reason for which this reasoning doesn't hold.
I don't know. I mean, might work, but I see sort of little benefit from that. And I mean, also kind of, I mean, because kind of the privacy law still grows with kind of around root K. So, I mean, you wouldn't be using millions of compositions typically, because kind of then the privacy laws just would start degrading. So.
Okay. All right. So thanks again for the talk. Really interesting. And we are good for today. And we'll see you all again if you want to join us next week for another talk.